Only you're going to see me solving problems, and they're going to be slightly different than the ones in the afternoon. So check this one. I made sure. Maybe somebody needs to Zoom and make sure that you can hear me. Can you hear me, those who are on Zoom?
Yes, yes.
Okay, perfect. So I always want to do that. In any case, so just keep that in mind. I'm aware that is without voice, but there was nothing I could do. It was too late when I realized that the voice was not on. All right, so I have changed a little bit the presentation of the main page just to make it easier for you. And I put it in this format so you can see whenever you click, for example, on the week, you're gonna go to the module, but whenever you click here, the ones that are underlined, you will go to, with the exception of today that I have to load after this afternoon, you'll go to the video recordings, all right? And then I will add one line where you're gonna see for homework that has a solution practically. I'm gonna put the homework and the solution underneath it so for you to go, but I will not add any more to this page. Okay, so going to our module for today, as we had discussed, we are gonna solve problems, but what I wanted to do is also put a page that includes the vector operators, vector identities, and all of this. I keep that there for you because everything we're gonna do from now on, until you know how to find this material, you will have to use it. And we are not gonna slow down to review it again, all right? This is material that you had before. So we're gonna try to use it, but not necessarily cover it. So I'm gonna have it here in case you wanna just quickly see what it has. But we are gonna start with examples on Coulomb's law, and we'll talk about electric fields, and then we're gonna look at different cases where we will have to solve for the electric fields. And what I would like to do today is that go slowly through one solution, primarily because I want to show you how to deal with units. And but as we move forward, we are going to speed up a little bit. All right, so this is what I covered with other classes, and you're gonna see also here. But I just wanted to remind you of what is Coulomb's law. Coulomb's law is really the one that gives us the force when we have two charges. In this particular case, I had two positive charges, identical, and then I wrote the electrostatic force that is exerted on each charge, and I put here the formula for it. And then we said that while the force is something we feel, the electric field is what we are working with. Because when you talk about a force, you really have to have two charges, your source and your observer, all right? In that setting, everything that counts are entities that have a charge. Eventually, when we go to grounds and other metals and stuff like that, you may bring something near a charge that is not charged itself, but in the presence of the field that is exerted by the charge, then you have an induced charge on these conductors. And this is an important thing to remember, so we'll come to see that. But for now, anything that we bring into our space will be charged. So two charges here, you see the force, and then from that, how we define the electric field, all right? So here, we've seen those things. Now, what I would like to do, first of all, is to start with the example. We'll solve both numerically and in units. A simple problem that says, for example, this one here. We have a charge, and then you can see the picture here, which is for the most general case, but we have a charge which is 5 picoseconds. Picoseconds. I was trying to solve a problem with data, like bit data rates, Everything was in seconds, I apologize. So a charge that is 5 picocoulombs, and that charge is located at the center of a Cartesian coordinate system. So let's take the most general case here that you see is a charge. And then what we have seen is that the electric field that is produced, the electrostatic field that is produced by this charge is given either by this form, where now this is the unit vector, as you can see here, all right? Or it can be written in this form, where we have replaced the unit vector by this one. And people have asked me multiple times, why do you not go to 2 instead of 1? Well, now in 2 is more complicated practically, because we have a third power in the denominator, plus we have another bigger vector. And the answer you're going to see it below, because from the computational and mathematical point of view, it's easier to deal with expression 2 than expression 1. Okay, so now we come to this problem where we have a charge of 5 picocoulombs located at the center of this coordinate system. Now, one question for you. You saw how I put my coordinate system? Yes.
Why is the magnitude or square for equation 1 the other one is
because of this one. This is how we define the unit vector along the direction of a vector r.
Oh, so you just took it out.
I just substitute for it. Exactly. Okay. So going back to my question, we have a coordinate system. Okay. So question that I have for you, I put the coordinate system here the way you see it. Right here. Could I, how would you put the coordinate system? Why did I choose it this way? Was there a particular reason, or I'm used to it? The origin, I said it arbitrarily, but how I place the order of X, Y, and Z. Is there a particular reason? I don't use what? Yes, there are 2 ways of standing up coordinate systems. The positively defined and the negatively, like the clock, all right? There is a clockwise and counterclockwise. So we don't have that here. We have a positive and negative order kind of approach. The positive is like what we normally always follow with the right-hand rule. You remember the right-hand rule? So tell me cases where we use the right-hand rule.
Like a current running on that.
That's that rule.
Oh yeah.
No, it's not right hand, both of them. But this one,
The
cross products. And so this is extremely important, all right? So when you stand up a coordinate system, you always use, don't go from one for the positive to negative, because you will never know if you use one ordering the positive, then you have to use the same kind of ordering for all of the cross products. All right, so what I do, this is my ordering, counterclockwise. All right, you see it here for me. When I see it is counterclockwise. All right, if this is my, okay. Let me see here. here. If this is my X, which is coming towards me, this is the Y that goes to my right, and this is the Z that goes upwards, all right? However I orient it, it has to be like this, counterclockwise. Now, why is that important? Because on that system, X cross Y equals what? X, unit vector X along X cross. Yeah, it's the unit vector across along Z, all right? But if you use this, if you use a different, the opposite here, and then you use this one for the cross product, you're wrong, all right? So always use the same thing. That's why it's X, Y, and Z here. You always make sure that however you set it follows that rule. Okay, now here what we do is the following. First of all, what I have to is they ask me to find the field at point A. So point A is right here. All right, and the what is vector R? Vector R here is vector R is OA. You see that? Okay, is the vector who connects the source, the charge, to the point where I want to find the electric field. And then now if I know what points define R and the direction, then how do I calculate the vector from the coordinates that they have given me for A and Z and O? See, they have given me the coordinates. So according to that, OA, which is R, is going to be, remember when we wrote this before, AX, and then is the X component, the X component of point A, which is 3, minus 0, obviously. All right, so it makes it 3, just to make it. So it's 3 AX for the same reason, plus 4 AY plus 2 AZ. So now I have a vector here immediately. So since I have a vector, I can find the magnitude of this vector from the square root of the squares of the 3 components. So 9 plus 16 plus 4, which I have down here. All right. So I'm gonna just make it a little smaller here. Remember, why it's easier to work with R? Because I know both the vector R and I know its magnitude easily. Okay, so now I'm going to the expression that I have here. All right, this is equation 2, and I plug in things. But see, everything that I've given you is in, has units. Charges in coulombs. Epsilon sub naught is called, you remember where we talked about that, is the electric permittivity of the medium. We are in free space unless, because I have not told you otherwise, right? Whenever I don't tell you anything about the medium, you assume free space. And the electric permittivity of free space is epsilon naught. And we know the value is 8.854 times 10 to minus 12 farads per meter. What is the unit farad used for? For what kind of electric circuit component? Capacitor. So it's epsilon sub naught is like a capacitance like a density though. all right? So it's a density. So that's why it is capacitance per meter, farads per meter. But this is equivalent to, it shows the capacity of the medium to store charge, period. That's what it is. Then R, which is the vector, is in centimeters because we have given all of the dimensions on the coordinate system in centimeters. And therefore, here is what I want you to do when you make calculations. Put all of the numbers up front. Make sure then you take all of the units and put them in a parenthesis. And then as you work with the numbers, you also work with the units. And you try to also make sure that when you work with the units, as you do with the numbers, you try to convert to common units. So if, for example, we have farads per meter and then you have centimeters, obviously at some point you have to convert centimeters to meters or meters to centimeters. Somehow you have to do that conversion to be able to simplify things. And then if you go through this, you find not only the value of the electric field and its direction, but also you find the units. Now, the majority of the students in this class do not use units. They give values, and then the units at the end comes as an afterthought. And you know what happens? I never give them credit for this. I subtract a lot of points. And why is that? Because a value for the electric field without units is useless. Because, for example, if you give me this value and you throw a unit like volts per centimeter, the same value. So if there are no units, I don't know what you're talking about, obviously. It could be anything, all right? I could imagine kilovolts per meter, or it could be volts per meter. And then the difference between kilovolts per meter and volts per meter is 10 to the third. 1,000 times difference in the value. That's why I don't consider a response without, in these units, without units next to it, I don't consider to be, I consider to be incorrect, even if the number may be the same. Now, a lot of time, most of the students, therefore, who do not do this well, they belong in two categories. Some students who give it without any units, and some students who give it with wrong units, because they try everything, all of the math, the calculations in the beginning, and then they try to figure out what the units are. Well, that's wrong, because from trying to work with the units, it will introduce some other powers of 10 if you have to convert. And that is going to change your value, right? So do it the way I show here. This is how I want you to do it in your homework. This is how I want you to do it in your meter. This is how I want you to do it in your final. In the homework, I will be particularly critical if you don't do units. Because for homework, you don't have a time constraint like you have in a meter or in a final. But even in the meter, I prefer that you lose time by trying to do something correct instead of going hop, 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 and then you do a little bit of everything that is all incorrect. Okay. All right. Any questions about the approach I followed? I did that very carefully because I want you to do the same, please. And also when you write clearly. That is my biggest problem a lot of times. I know that each one of us has a different way of writing things, but please write them clearly, because it's not just for me, it's for you too. If you write something and you cannot read it yourself carefully, you don't know what you wrote, because something looks like 2 or 7. And then later on, days later, where you have to go back and see what you've done, you don't know whether it was 2 or 7. I had that case. That's why I'm using all of this. All right. So, yes.
So we lose points for every single step we
No, you lose points if you don't have units or if you don't have the correct units. And for you to have either units or the correct units, you need to do it the way I did it here.
But it has to be on every step, not just the next step.
I'm not, you know, that is not important, but I'm telling you, if you don't do it in every step, most probably the chances of doing the right units, especially in a complex problem, are going to be very slim. It's for you rather than for me. If you skip steps in the units, most probably you're not going to have them right. Do you know why I'm saying that?
I get what you're saying. However, personally, having the unit becomes more of a hassle that throws me off. That's why I'm just confirming if I have to actually write all the units.
How are you going to compute the units then if you don't put them next to your numbers? How are you going to do them separately somewhere else?
I tend to write multiple steps in the same line of equation. And then by the way I will mentally keep track of everything works, and then I write the units on an occasional step when I actually have a mental break. So I usually wind up writing units for maybe one step per 5.
Okay.
But I'm trying to confirm, do I actually lose units for every step or just for having it down?
You know, I will say, let's talk about two different things, all right? One is how I'm going to grade you, and the second is how, what is a good habit to acquire when you do this kind of work. When you do this kind of work, a good habit to acquire is put units, and you have to come down with it at every step. I do that, and I am, you know, 3 generations over you. And I'm working on this since 72 when I got into college. And I still do that because it's good practice. It becomes part of your thinking. You don't have to get distracted anymore. You know, it's like when you play the piano and you have to, you know, hit another key. The fact that you have to hit another key that is out there should not distract you. You have to, otherwise, you know, you're not going to play the song right. All right. So you have to learn how to do it right. Because in simple problems, you're going to have, it will be okay to skip a few steps and then put your units at the end. But in more complex problems, it's not going to be okay. And most of the time, you're going to come out with the wrong solution. There is another thing. If I need to see your work most of the time, all right? And sometimes getting the right units is not an obvious thing. So if all of a sudden I don't see anything and at the end I see a value and the right units, I will wonder how the whole thing came out. So try to use your logic. Try to ask yourself, if you were in my position, what would you like to see? And then act accordingly. So, but I cannot tell you that I will be so bureaucratic that every time you miss a comma from what I thought, where I thought it should be, I'm going to penalize. I don't grade like that. All right, my grading is different. You're gonna see it. I'm grading in a different way. I'm not grading like in lower school, lower like in K to 12, all right, where you miss a word, you know, out. No, I'm looking. What I'm trying to see is that, do you know how to solve the problem? Have you given me evidence that you know? That's the 2 questions. And, you know, there is not exactly golden rule, all right, on how to get into that point. But you will see how I do that. Most faculty, that's how most faculty grade. In any case, if you have more questions, let's talk about that individually, yeah? All right, so let me now go to the next topic, which is, okay, we did 1 charge, let's do now 2 charges. And let us try to find the field from these 2 charges. So what we use there is something you have also heard, which is called the superposition theorem. What does that say? That if you have 1 static source, a charge, and then it generates an electric field, and then you have a second static source, a charge, and generates its own field, then the total field is the sum of the 2. And when I say sum, I mean the sum of the 2 vectors, all right? Because each field is a vector. Okay, that is called superposition. It applies to as many sources as you may have. If you have 100 sources and each one of them produces a vector field, electric field, then you can sum these 100 different vector fields, and then you're going to find the total. All right. So here I give you two charges, a red charge, Q1, a green charge, Q2. Both of them are positive. All right. One is 5 microcoulombs, the other is 2 microcoulombs. I give you the points where the charges are with the 3 coordinates. And I'm asking you to find the total field at the center of the coordinate system. So, as I did before, I will do now. First of all, what I do is I calculate the two vectors, R1 and R2, all right? And they are both here. And I calculate them from what we know about how to find vectors, all right? When you know the points, the beginning and the end point. All right. Now, since I have the two vectors R1 and R2, I also have their magnitudes, okay? So what I do is to calculate the field at 0 from Q1, E1, a field at 0 from Q2, E2, and then to sum them up as two vectors. All right. Now here, what I did in the morning is to remind everybody how you find a vector from A to B, all right, where you know the direction is from A to B, you know A coordinates, you know B coordinates, and then you use this formula to find the vector. So that was the parenthesis, so people can remember. And if you use this approach, then you find the two vectors for our problem, R1 and R2. Okay. So now, using the formula 2 that we saw before, I calculate one field E1, red, coming from the Q1, red charge, E2 coming from the other charge, Q2. And the way I find the fields, which is also interesting, I find them in their corresponding coordinates, all right? One has an X and Z component, like the red one. The red field has an X and Z component. The green one has a Y and a Z component, okay? So how do you sum the two vectors? Here, what we have accomplished that makes it easy, we don't do it geometrically, you do it mathematically, because I have already converted each vector to a common coordinate system. All right, so I know the components of each vector. If you know two vectors by their components in the same system, then to sum them up, you sum their individual components, all right? And in this case, so I sum, since there is only one has A sub X, it's here. And that comes from, in fact, if you wanna see, that comes from the red. There is only one Y component. It comes from the green field. And then it has two Z components. One comes from the red vector, the other comes from the green vector. And then you combine the two and it gives you this expression. And this expression has all three components and of course units. And for these units, in my case here, as you said, if you don't do them at one step, do them separately. but I want to see the separate done, and then you put them together with a value, because here, if I did them separately, and I put the units for the charges here, I put the units for the vector up, the units for here, the third power of the vector down, I put the units of epsilon naught, all right? And then I have 1/centimeter squared because I simplify things. I change centimeters to meters. And then what happens here, I find 10 from the units now, 10 to -2 volts per meter, which are the units of the electric field. And therefore I add them here. And you see that the 10 to -2 is gonna change the value. So if you don't do the units, you practically make an estimate of a value which is 100 times higher than what is supposed to be when you measure it in volts per meter. And that's why it is important to pay attention to units. Okay, any questions on that? Okay, so now we have an interesting thing, and then I would like to expand on it for a moment. So I will add here a page. Let's assume I'll give you a more general problem, and then we'll go back to the specific, because we're gonna, maybe I need to, okay. Why do I then do it here? So since we have space. So here I'll separate that. And now I'm doing the following. I give you two charges without a coordinate system in there. I say I have one charge here, which is positive. All right. And is positive. And is Q. And I give you another charge, which is also positive, and it's also Q. And in this particular case, I will only give you the distance between the charges. All right, so I will tell you that this is a vector R and put it here. And this vector, all right, which I define it like this, I'll tell you that this vector is R is, say, 5 AR centimeters. Okay, so I gave this problem in a different way. A is a bar. All right, so let's see how we're gonna think about this. And we discussed a little bit that in the morning. Before you go to try to solve a problem, you need to get a sense of what is it that you have and what is it that you have been asked to find before you start writing. And then try to use any information you have. So you try to envision things and then try to get additional information, not from your math, but from the physics that you have, we have discussed and then you have learned, all right? So this is fundamental, because if you go immediately to math without having had that kind of thinking ahead of time, then you're gonna get some kind of a number. It might be, most probably will be wrong, and you will have no idea why it is wrong, all right? In engineering, it is intuition, which is what you're gonna try to develop through those exercises, all right? When you see the problem and try to understand what possibly the solution is gonna be without doing math. This engineering intuition is extremely important in design. As I said in the morning, before the war, people were designing radars that were working, all right? There were no computers, there were no calculators, there was nothing. It was only handwriting. But they were designing extremely complex systems that were working. So how were these people designing those complex systems when to get the logarithm at the time, you had to write an expansion, a series, and then calculate it by hand, all right? There were some kind of, rules, like the logarithmic rule. There's something that people were using at the time. But other than that, it was, why did people design that? Because they knew what was working. They knew what they had to make it work. They had it all here, that for this thing to work, it has to be in that particular way without having the math to tell them that. Math is only to either verify your intuition or to give you some more specific details. So let's try to think about this problem without writing math. Okay. So first of all, I'm gonna erase this, or I will rewrite down here the charges because I have to be clean. I don't want to be distracted by lines and so forth when I'm thinking. At least that's how I'm working. When I'm thinking, I don't want to have too much distraction. Okay, positive, both of them. Now, if those, let's see what we know. You have two identical charges, even if they're, or forget about being identical, that is coming second. When you have two charges which are both positive, which direction the forces will apply to them? Opposite. So one force is gonna force this to go here, and the other is gonna force it to go there. All right. Now, if that were by itself, if for a moment, take this out, say copy, and then I will remove it. In fact, I should have said cut. Okay, for a moment, if that were by itself, how much would the electric field go? The electric field would have gone like this. All right. Now I put the other one down. Okay, if I put this here, it's electric field. Let me use a different color for a moment. Oops. Its electric field here would go like this. All right. And now I have these two charges and I want to find out what happens in between them. In between them, if I go as an observer, I will see two electric fields that are opposing. All right. If I am closer to one charge, so if this is me, for example, here, and then if I am right here, closer to one charge, then I will see an electric field stronger from this blue charge than I will see the electric field from the pink charge, which means that if I were to translate those into forces, the force that I would feel from one charge will be a lot stronger because I'm closer to that than the force I will feel from the other charge, all right? And if both charges are positive, and as an observer, I will always assume that I'm a positive observer. In this case, since I'm just decided to put myself in there, I will feel a force that is pushing me away from the blue charge, which is much higher from the force that is pushing me away from the pink charge, which means that I will tend to move towards the pink charge until, and that is going to change until I get into the middle. And what happens here when I get in the middle? Then the two forces that push me away from both charges are equal, which means what? That I don't feel any force. Or equivalently, you can say that the electric field at the center, the total electric field from the two charges at the center is 0. All right, you don't need to write any equations to say that, and you don't need to take this much time to think about it. All right, so practically, I could say that the field at A is 0, and you can write all of the equations and prove it. But this is what I would say. Now, the next thing for somebody to ask is what happens if instead of A, which is in between, so here you can see I have already placed a coordinate system. And when somebody is giving me a problem without coordinates, then I have the right to select the coordinate system that fits me best. The easiest, the best coordinate system is one where Q is at the 0 at the center, 1, Q. The other is along the Y direction, and then A is along the same. So it gives me the simplest, all right, arrangement. Now let's assume that I go along the Z-axis and I arrive at point B. And the question is, what is gonna be there when I am an observer and I go in between the two charges? Is the field gonna be 0 there? No, and let's think about that without writing any equations. If I am at B, then the field that I will see is gonna be this one from the charge, the red charge. And the field that I will see from the green charge is gonna be this one. And these fields will be different in direction, but they will have the same magnitude. So then, what is the combination of the two? What is the superposition of the two? What is it gonna give me? It's gonna give me exactly an arrow shooting up or an electric field that it has a Z component only. So now I understand that if I have two charges, see what you thought about this problem, that if I have two charges that they are identical, then at the center of the line that connects them, there is no electric field, but then there is only a vertical electric field, which means that if I was a free, say, charge in there, ready to move, for example, you will see that the charge will be forced to go up or down, but along the vertical line, all right? Because that's how the force, it feels along that direction. And when you see, in fact, how you plot the electric fields, you will see that the way they plot the electric fields around those charges is like they have 0 value at the center. We'll see that later. So that is a problem here, but let me, a problem you can think like that. Now, after you make all of these conclusions, then you can sit down and write your equations to confirm that this is correct. But you don't need, if you don't have that in mind, and then you write your equations, and then you go and you make a mistake somewhere, which is very easy to make, like in the calculations, and you find a value in the electric field, you will accept it if you have not done this thinking before, all right? Let's assume that now I have two charges, but I consider them to be in a three-dimensional space in the following way. So you have a charge here, all right, 1. And then you have another charge here, the same, for now, 2. And then I would like to see how the electric field, if I, for example, the question is, how, if I were to describe, if I were to consider this, let's assume that I had asked you the following, to consider this vector or line that connects the two charges, and then consider a plane that goes through I will do it in 3 dimensions. All right, a plane that goes through the center, and I would like them to show me how the electric field goes from there. On this plane, how the electric field changes both in direction and in value. All right? You can solve this problem from what we've discussed without writing equations. So who is going to help me go through this for a moment? Let's think about this couple of minutes, and then I would like somebody to give me some directions on how I'm going to think about that. And in fact, I will take this green and do it also like this, in case we want to write here. And let's assume that if this is point O, this point is here. So this is the plane. Below this plane at a distance is Q here, the blue Q. And then above this plane is the green one. Okay, below is the blue, above is the green. And I would like to see the field on this plane in direction and value. So what do we know immediately? That what is the field at 0? 0. So we know that it's going to be 0 field. What is the field along this line? Which direction does it have? Okay. Okay, so from here up is going to be smaller, starting smaller, and then growing. Okay, that the size of the arrow shows they grow in the increase in the value, right? From 0. Okay, how would it be below it? Up or down? Down. So here. Okay, how about the other 2 directions? Without thinking very much. How are they gonna go? What is the problem? The problem has some kind of symmetry. What symmetry is in this problem? Cylindrical, along this axis. Whatever it happens along one direction is going to happen along any other direction, because it does not matter of which, side of the axis I'm looking at it. So that means that the field is going to go. Let me erase that O is in the problem that I have. So this is the center, right? A field is going to go radially like this. All right. And so, and from the other side, the same. Okay, so practically, on the basis of what you know, you solve the problem that if you wanted to solve mathematically and using any kind of coordinates, it would be hell. Going from one set of coordinates to cylindrical and wherever else you wanted to go. All right, so you solve practically the problem. And now that you realize that it was also cylindrically symmetric, you don't even have to go and find it anywhere. You just find what the value is only here. How it changes, and then you project that everywhere. That's what you have to do in most problems. So I would like you, every problem we have to solve, to try to think think, you know, of how this is expected to work, and then try to use math to provide more detail about it. That's what we are going to do in this class. And a lot of times, some of these examples that we are going to start doing in the class, all right, that is going to be more like this, is going to be just to force you to think that way without doing math. So we're going to start that sometime next week, all right, with doing these kinds of exercises here. Any questions so far? Okay, no questions. Good. So I will see you on Monday. And those who want any questions about homework or anything else on Sunday. Okay.
Well, it's just the team exercise homework. So for number 2, the problem with the circle, when you're thinking about the when it gets more illuminated, I'm trying to picture how I should be thinking about it. So I'm thinking of like a dot, and the brighter it gets, like it almost looks like a star in the sense that where if you look at a star, it's kind of like.
What is it asking you?
It's just asking what the
divergence. No, what did it say? No, that's yeah.
Assume that you're looking at the cylindrical shape of a sphere below it made up of explain what you would see if your eyes were recording in illumination only and not the values. So would it be a star shape or no? Okay.
It's gonna be, think about that. So divergence measures the change in derivative. The change in, excuse me, it measures the change in the value. It measures the derivative, all right? That's what it tells you. So if illumination, if they like the field, all right, this has the same kind of color everywhere. That means that it does not change. The derivative there is going to be 0.
So there's no change.
Well, only the white, and there is no change in the blue. Where is the change?
Those two?
Exactly where it goes, right at the line where it goes from white to blue.
Is this like I heard something about this where, is that like, never mind, actually, I think this is something random, but that someone said that if you looked at light around a massive, like a huge mass, that it bends.
Well, that, yes,
I
mean,
no.
This happens in space. Here we are down to Earth.
Okay.
Yeah, space, I said you sent me a question, all right? In space, because of relativity theory, all right, which we don't see here, huge mass and energy bends space-time. Why is that? Because we measure time and space with respect to an observer. All right, and then we are here all moving with the same velocity, all right? Our system moves with the same velocity and we move with the galaxy. And on our point of reference is like moving with us whatever direction we are moving. But if you are in space and you are a photon, like light, and then your point of reference is moving with a different direction, in a different direction and different speed, then you think you go straight, but with regards to that point of reference,
you're like bending.
Oh, yeah, so that's what relativity theory says.
Oh, okay.
Which does not apply to us because everything moves with the same.
I just have a quick question.
Yes.
So you mentioned that the electric field going up would get bigger. From what I understand, like electric field, I thought it was like a sphere sort of thing, where it's coming out of the charge.
Yeah, but the charge, that's a sphere, but here we have 2 charges and we're not looking at the sphere, we're looking at this plane that is just at the center of the 2 charges.
Okay, yeah.
At the center, the total field is 0, but that's because it cancels out. But as it moves away from the center, it cancels less and less, and that's why it grows.
Oh, okay, so these are both still superimposed.
Yes.
Oh,
yes.
okay, that's so confusing. Because I was like,
of course.
It's at the edge of it.
Yeah, no, it's superimposed. Yeah.
Yeah, thank you so much. So, like, why does it come out like that? Like, why does it like become less and less out as it goes out?
Because here, up here, you see how it happens? As you go, when it's down here, these are up in the opposite directions. But as it goes up, these go more and more like this. And as they come closer, the sum of the two vectors, you know, is going to become bigger until they are along the same direction, which is at infinity.
Oh, okay.
Right?
So they kind of like come together.
They come together eventually. That's why it goes from 0 to whatever it is when they come together. All right? It has to go from 0, whatever it is when it comes together.
Oh, okay. Thank you. That makes sense.
Sure.
I had a quick question.
Yes.
For our team assignments,
Yes.
do we all submit
One.
one assignment?
Mhm.
Okay.
And you write the names of the people who have participated in the solution. Because if somebody is at like an MIA,
Yeah.
you don't, all right? You want,
Okay.
you want.
Okay, thank you.
Sure.
I meant to ask about
Yes.
the team assignments and what
Yes.
sort of resources you expect us to use to, because
It's open book, open everything. As long as whatever you tell me is correct. So you're going to be responsible if you go and look at other resources, which is fine with me, all right? But make sure whatever you tell me is correct. So you're going to be responsible for the quality of the information.
right, I realized that most of the questions in class are apparently remote from the content of the class almost. Like first assignment, for instance.
Well, it is because I want you to start thinking of what a divergence is. I want you to start thinking about derivatives rather than absolute values. All right? And that is critical when we solve problems eventually. So it's like for you to visualize why do we use like the divergence later? And if you cannot visualize what a divergence is, you're not going to be able to understand why later it gives us specific things.
Because the first group assignment, for instance, asks questions like what happens in space if you have no suit. And
Yeah, this one is because, yes, because we talk about forces. All right, and you want to see when you go out there, there are forces from inside and there are forces from the outside, but then there is also the lack of, I mean, this is a very interesting because most engineers think that when you go into free space, you explode,
some of the parts in it, yeah.
which is not true. You die before you explode. When you die, you're dead. You cannot die twice, all right? I mean, everybody thinks that people explode and they don't.
I'm trying to figure out what would kill you first, the hypothermia from lack of heat or the air being sucked out of your lungs.
Yeah, the air sucked out.
Probably,
I think the lack of oxygen.
Yes, the lack of oxygen.
Yeah, but I was just curious if there are any recommendations you have for
You
veritable
can
sources.
look and find. I mean, of course. I mean, if I ask you something that you don't, go and read about it.
I did. That's how I
Perfect.
just wanted to make sure that those sources were veritable enough for you.
Of course, you know, this is whatever I give you. Have you seen saying that don't use only your book, you know, do that. I don't give you any guidance, which means go and use whatever you want. And that's true throughout the class, but make sure that you check your sources.
Thank
you. You're welcome.
Yeah, this.
Just have one last question about Top Hat. So are the assignments and the quizzes supposed to before the class starts?
Yes, and as a matter of fact, I need to thank you for reminding me, because what I have to do, go here, go to Tabhat, go to Tabhat, and I'm gonna send a reminder. Unassign the exercise.